Hi everyone, I'm Eric Cambria from NTUC CDS, and this is the course on Understanding Retrieval-Augmented Generation, or RAG. This is based on the homonymous book, which is a revisitation of Chris Manning's Introduction to Information Retrieval. So during these 5 lectures, we're going to be looking at basics of information retrieval and finally talk about RAG and agentic RAG. So in this course, I'm not going to talk much about LLMs and word embeddings because these are covered in this other course that I strongly recommend you to look at if you haven't. So what is information retrieval? You can think of it as when you're studying for an exam, you're absorbing knowledge, wisdom, to then be able to retrieve it when it's relevant, when you need it, for example, to take the final exam. And information is really the main treasure of mankind. It's all about being able to collect the relevant data and filter out the noise. And so information retrieval actually is a classic topic that has been studied for decades, which encapsulates many other tasks. And ultimately, it's about satisfying the user's information need, including things like question answering, text summarization, topic modeling, plagiarism detection, trend discovery, sentiment analysis, and more. So let's look at the quick timeline of information retrieval. We started with keyword-based approaches, which is what we'll talk about in this lecture, like one-hot encoding, where we were basically just focusing on the presence or absence of specific keywords to retrieve relevant documents. And then we went on with more stats-based retrieval. This is what we're going to talk about in the next lecture. So how to come up with the rank for every document to decide whether how relevant they are to a specific query based on statistics. And then later on, we started looking at more semantics aware methods based, for example, on word embeddings. And finally, today, the state of the art is RAG, Retrieval Augmented Reality, which is the concomitant use of large language models, generative AI, with the old school information retrieval techniques to be able to find whatever you need on the web and answer your queries. The future of information retrieval is agentic RAG, where you have all these agents that know you well and can do all these tasks autonomously. So we're going to be looking at different ways of representing documents. In this lecture, we'll start from the basics, one-hot encoding. Next lecture will be about bag of words. And word embeddings is something that we talked about in the previous course. Okay, so let's get started. What is Boolean retrieval? Let's say that you have a query like this. You want to find all the plays of Shakespeare that contain the words Brutus, Caesar, but not Calpurnia. So you may think of maybe taking first all the documents that contain both Brutus and Caesar and then strip out the ones that contain Calpurnia. But that's not very efficient, right? It would take a long time to do that. The best thing to do, which is the whole concept of information retrieval, is that you create a model for your documents, and then whenever you query the system, you're not actually querying into the collection of documents, but into the model of your documents. How can we create such model? In this course, we'll see sophisticated ways of creating these models. The simplest way is to do this, encode presence and absence of different words within specific documents. So we're looking at the plays of Shakespeare. We have 6 documents. The columns are the documents. On the rows, you have the words that make up those documents. So this is just an example. Of course, we have more than just 7 words in this plays of Shakespeare, but it's just to understand how this works. So whenever I find the word Anthony at least once in the play, I put 1. If it's not present at all, I put 0. So this is why I said it's encoding presence and absence. This one doesn't mean that it's only present once. It can be there multiple times, but I don't care in this case. I just want to create a Boolean vector, ones and zeros. So this is good. Why? Because then when we have a query like the one that we just mentioned in the beginning, give me all the plays of Shakespeare that contain the words Brutus, Caesar, and not Calpurnia, I can convert that into a Boolean operation. This is similar to the concept that we covered in the first course, where we say that, like in the case of Fourier transform, we go from one domain to another, do some calculations, and then go back to the original domain. So here, instead of working directly with words, with documents, like we did for word embeddings, we are translating, converting words into vectors. How do we do that? Based on the model that we just created in the previous slide. So Brutus is what? Is 1, 1, 0, 1, 0, 0, because of how my model is engineered, because I'm only looking at the 6 documents, the 6 plays of Shakespeare. So Brutus is 1, 1, 0, 1, 0, 0. Same for Caesar. Calpurnia is complemented. So in theory, Calpurnia is 0, 1, 0, 0, 0, 0. But because I'm looking for the plays that do not contain Calpurnia, then I have to take the complemented one. So when I do this operation, which is very fast for any calculator, because we're just converting to ones and zeros, then I obtain another Boolean vector. What is this Boolean vector? 1, 0, 0, 1, 0, 0. It's my answer in this model, which I then have to reconvert to the original model. So 1, 0, 0, 1, 0, 0 is what? Basically is Antony and Cleopatra and Hamlet, document number 1, and document number 4. So this is the answer to my query. I didn't really go into the documents. I just used my model to answer this query. So this is the difference between having a model for information retrieval and just working directly with the documents. So if I ask a friend of mine this query, someone who read all the plays of Shakespeare, they will have to think through and maybe have read all the plays. But in this case, I'm not even looking at the documents. I'm just using the model that I created to answer this query very quickly. Because again, it's just Boolean operations, right? That's what computers are best at. Now, we only consider a very simple example with very few documents and very few words. In reality, you can imagine that even for a simple case like this, where I only have 6 documents, I would have a very tall matrix, right? Because then in reality, all these plays of Shakespeare definitely do not have only 7 words. They will have thousands of words. So this would be a very tall matrix. And most importantly, it will be a very sparse matrix. And we are not very good at working with sparse matrices. So how can I optimize this? Especially when I start having a lot of documents, then as I add more documents, I will have more and more sparse matrices. So what if instead of recording the Boolean vectors, I just focus on the ones? These are the things that I'm more interested in, right? The presence of a word like Calpurnia in a document like Julius Caesar. So a vector like Calpurnia, instead of encoding it as 0, 1, 0, 0, 0, 0, I can just say, okay, I got a 1 at position 2. This is what an inverted index does. So instead of having Boolean vectors that are of a fixed size, instead I have this index that just tells me where the ones are. So for example, this vector 31, 54, and 101 tells me that of all the documents I have, which could be like definitely more than 173, The word Calpurnia only appears in document number 31, document number 54, and document number 101. What happens if documents change and there is a new word that appears? Then I will have to add it in the right place. I cannot just append it at the end. If suddenly the word Caesar appears in document 14, I will have to add it here between 6 and 16 because of how the inverted index work. Why? Because then we have to do some operations like the merge operation to find commonalities between these indexes. But so this is where we're at now. We have our dictionary, our list of words, and then we have the postings that represent where these words appear in my collection of documents. So the ways we build this dictionary can be more or less sophisticated. I can just blindly add any word that I find, or I can do more sophisticated stuff like doing some lemmatization or stemming and case folding and so on, removing of stop words and so on. So for example, here, if I have a very simple document that just contains the words friends, Romans, and countrymen, I can use a tokenizer to remove punctuations and find the specific words. Then I can use some linguistic modules like lemmatization to remove plurals, for example, or even case folding, because otherwise I would have the same word friends with capital F and small f in my dictionary, which is not what I want. That's why I need to do a bit of pre-processing. Again, these are things that we discussed in the course of understanding NLU. But ultimately, I'm left with this inverted index. So let's see exactly how to build it from scratch. Let's say that we have these two documents. How do we build the inverted index for these two documents? I start by listing all the words that appear in each document one by one. So I start with document 1. Every time I encounter a new word, I just list it and I specify where it appears. So after I finish with document 1, I continue with document 2. And then what can I do? I can order them by alphabetical order. So it's easier for me to see what's happening here. For example, I can see very quickly that Brutus appears in both documents, and then some words are repeated and so on. So a better way to represent this, as we said, is using the inverted index, which is a list, like a Python list that contains the IDs of the documents. So don't get confused. This 2, for example, doesn't mean that Brutus is contained in a document twice. It means that it's contained in document 2 at least once. And here I can also save the frequency of the word Brutus in my document collection. So this 2 here means that the word Brutus appear in 2 of my documents. Why do we need this? We'll see it later. I can save it as metadata, or I can anytime find the length of this list by using, for example, the len command in Python. So why do we need the frequency? We'll discuss that later. But then this is what I get after collecting all the words and presence of these words in 2 documents and reordering by alphabetical order. I get this, which is a much better way than just using the original Boolean model. The problem is that now, how do I do those beautiful Boolean operations that we saw earlier? So we said that we do all this because then a Boolean operation like this is something that my computer can do very, very quickly, very easily. And now we don't have those zeros and ones anymore, right? Because we converted our model to the inverted index. But this is an operation called merge operation that is also very easy to do for a program like Python. You're just basically looking at 2 lists of numbers and find the ones that are common. So in Python, it would be just using the AND command between list 1 and list 2 and represent it as a list. It would give me the two common documents that I need in this case, where my query is find me all the documents that contain both Brutus and Caesar. What's the problem of Boolean query is that it's only good to find an exact match. So if you're doing a search query on the web, it's pretty useless, right? We'll talk about this later in lecture 2. But if you're looking for something in your computer or in your email, so you're looking for an email or a document that you remember it exists, then this is still very good. There is no point to use more complex algorithms for this. And that's why, for example, even today, your macOS Spotlight to find documents in your computer works like that. Or even when you search for emails in your mailbox, it's also done by Boolean query. So now let's look at some optimizations. So how can I make sure that if I have a long query like this, it's in the best possible order? How do I, for example, do a bit of pre-processing to reorder this query so that it takes less time for my system to answer this query? As it happens many times in many computer science problems, you have to start from the most constraining variable. So if I have a query like this, Brutus and Calpurnia and Caesar, before I even do anything, before I go into my model and do those merge operations that we just talked about, I want to reorder this query so that I start from the most constraining variable. Which one is it? It's Calpurnia, right? Because then if no document contain the word Calpurnia, then there's no point in go and check Brutus and Caesar, right? So I start from the most constraining word, Calpurnia, that only appears in 3 documents. And then if that is true, I continue. Why? Because a Boolean operation made of AND, it's only true if all the items are true. So I want to check first the most constraining one. I would reorder this query as what? Calpurnia and Brutus and Caesar. And this is something that I can do quite easily because, first of all, we kept the frequency before, right? But also, as I said, that's something that I can get very quickly in Python or many other programming languages because it's just the length of that list. Again, we can say those inverted indexes as lists in our system. What do I do when I have also OR operation? So when I have an OR operation, I have to look at both words, and so I would have to consider this as a summation of the frequencies, and then I proceed as we said in the previous slide. So first I do the ORs, and then I proceed in increasing order of OR sizes. Anyway, if you don't understand this, don't worry because we have some tutorials about this. So what do I do when I have phrase queries like this, Stanford University, or names of people or name entities? So again, this is something that we talk about in the previous course of understanding NLU when we talk about concept extraction and name entity recognition. Look at 2 possible options for this. First attempt would be to have a separate dictionary for bywords. So I would have these 2 word windows that I slide through my documents, and for each of them I get a byword for which then I can build my own separate inverted index. Now this sounds like a good idea, but actually it's not that good because then who tells me which ones are the good bywords and which ones are not? If you have a simple query like this, Stanford University Palo Alto, and you slide your byword window through this query, you find 2 bywords that are relevant, Stanford University and Palo Alto, but then, for example, University Palo doesn't mean anything. So in theory, you can find which bywords are significant and which ones are not, because then a byword like this would most likely be not found many times in the rest of the documents, but still can be tricky and also ambiguous sometimes, because then you see in a situation like this, she may miss world tour. I can get a byword like Miss World that doesn't really have anything to do with the current piece of text. So that's exactly why this solution is more popular, positional indexes. This is also something that we discussed in the previous course when we were talking about transformers. So this may look like a very stupid way of encoding documents, because it looks like really like brute force. I'm just, for each document, I save at which position that word appears. So for example, this first row means that the word angel is present in documents 2, 4, and 7 at these specific positions. So this, for example, means that angels is present in document 7 at position 17. But this is still very good, because then it allows me to do more complex stuff. For example, when we do transformers, and also when I have special queries like this, to be or not to be, the only way to find documents that contain this exact sequence is to use a positional index. So is positional index better than bywords? Yes and no. You can use a mix of both. The problem with positional index is also that it occupies a lot of space, right? Because you see, for every word, you have to save all this information. So people look at combination schemes where you use, for example, a byword index for specific name entities, like names of people or names of products, titles of books, movies, and so on. And for the rest, you use positional indexes. Okay, now let's look at two empirical laws that can help us better understand our data. The first is the Hips law that helps me understand how my vocabulary grows as I keep adding more documents. So before we saw that we have only 6 documents and maybe hundreds of rows. The question here is, as I keep adding more documents, how proportionally my vocabulary grows with that. So before we had a very tall matrix because we had 6 documents and hundreds of words. As I keep adding more documents, how does my vocabulary size grow? Does it grow exponentially? Does it grow linearly? Lucky for us, it grows quite slowly. It follows a logarithmic curve. And so that's good news. And that's because as I add a new document, it's very likely that many of the words that make up these new documents are already covered in the previous ones. Another interesting law is the Zipf's law, which is also an empirical law that tells me what's the frequency of the terms in my document collection. So this can be very useful, for example, to find out what are the stop words that I may want to remove in my system. So you see that words that like stop words like the, of, and so on are the ones that are most present, and then they go down in a kind of a very, very fast. And so also the information that actually we have at the tail is very important for us. We'll see that in lecture 2, how to measure the rarity of some terms. So the Zipf's law tells us that the most frequent word will occur twice as often as the second one, 3 times as often as the third one, and so on. So this again can be useful to do some optimization. So to conclude this lecture, let's talk about some optimization techniques. First is skip pointers. How can we do the merge operation faster? This again is something that we can easily do with Python, but let's say if I'm working on hardware and I want to optimize my system, then one trick that I can use is that I will skip some sections of the lists that I have to check, because, for example, if I know that between 8 and 41 there is nothing for the specific word, then there is no point for me to go and check whatever is in between this gap, right? So this is how skip pointers work. To conclude, let's also look at some compression techniques. How can we compress our system, not just to save memory, but also to make it faster? So the two big questions are how to compress the dictionary, and finally, how to compress the postings. So compression is really important, not just for the size of your system, but also to make it faster. But here you can see that by applying some simple compression techniques like removing numbers, case folding, removing stopwords and stemming, I can really reduce the size occupied by my system that, again, if I'm putting it on hardware, it can be important. So what's a smart way to compress the dictionary? So in theory, I need to have some sort of table. For each row, I have my word and then all the information associated with it, like the postings, the frequency, and so on. Now, what if I represent my dictionary as a string, like this? This would save me a lot of space, right? But then how to know where each word ends and begins? This looks a bit messy, right? So instead, I can use numbers to tell me where each word ends and starts. And this is called blocking because I'm dividing my string into blocks. And this is useful because then if I reorder my dictionary in alphabetical order, then I can also do front coding. What is front coding? I use the stem or lemma of the word and then add the differences after the suffix or whatever else is needed to then reconstruct the original that you see here. So when you apply these two together, blocking and front coding, actually you can save a lot of space. Last thing I want to talk about in this lecture is the compression of postings. This is very similar concept, and it's the fact that when you have postings, which again are encoding where the ones are in your system, as you have bigger and bigger numbers, these occupy a lot of space in your system. But then if I just add the difference, the gaps between these two, I can save a lot of space. And this may sound like a bit too much just to save maybe a few bits. But then when I start having hundreds of thousands of documents, it's a big difference between saving this big number or just putting one. Okay, so that concludes lecture 1. Let me know if you have any questions, and if not, I'll see you at next lecture. Ciao.